It was a gloomy Monday morning, the kind where even your coffee feels cold. I had barely sat down to review last week's cases when a peculiar file landed on my desk. It was marked Case TSA 2025, the curious case of the vanishing sales.
The client, a retail chain, their profits were dancing up and down like a roller coaster, and nobody knew why. Every report, every dashboard told a different story.
Detective,
The client said,
we don't just want to know what happened. We need to know when and why.
That's when I knew this wasn't any ordinary case. This was a job for time series analysis, where time isn't just a background detail, it's the main suspect. Each data point, a clue. Each timestamp, a motive. And the answer, hidden somewhere in the patterns of the past. To solve this case, I need to understand how the values change over time, not just what happened, but when. Welcome to the world of time series analysis, where the plot twists are hidden in trends, seasonality, and sudden spikes. Let's crack this case, one timestamp at a time. Before I chase the criminal behind the crime, I need to understand the crime scene. Time series is no different. If you want to catch what's going wrong over time, you've got to study the clues hidden in how the data behaves. Let's start with the first suspect. Trend. A smooth operator. Doesn't cause chaos overnight, but slowly sneaks into the numbers. Look at this line steady, climbing over time. This could be rising sales, growing population, or a slow economic recovery. No surprises here, just a long-term direction. Think of it like the background music in a movie. It tells you how the story is evolving. Now meet seasonality, our second suspect. This one loves routine. Shows up again and again like clockwork. Peaks and dips, always around the same time. Maybe sales rise every December. Maybe website visits spike every Monday. These aren't random. Seasonality is like a calendar-driven ghost repeating its steps over and over again. Third on the board, cyclic patterns. Now this one's tricky. People confuse it with seasonality, but it doesn't follow a neat calendar. Cycles don't care if it's December or June. They appear, last for a few years, then fade. Think of business booms and recessions. It's like an uninvited guest. You don't know when they'll come or how long they'll stay. And finally, the wild card. Noise. No pattern, no rhythm, no motive. Just randomness, like static on an old TV. Could be measurement errors, unexpected shocks, a sudden storm, a surprise celebrity tweet. Noise doesn't follow rules. But here's the kicker. If we don't remove the noise, it'll distract us from the real story underneath. Together, these four characters shape every time series we investigate. To crack the case, we must separate their voices from the chaos, because only then can we predict the future and catch the culprit before they strike again. I had a lead. A new suspect had entered the scene. Temperature. And what I found surprised me. You'd expect that as the temperature rises, so do ice cream sales. Right? But in this case, the trend was going down. Strange. But let's not get distracted. If I only look at temperature and sales, what I really have is a classic regression problem. I'm not chasing time anymore. I'm simply mapping one variable to another, like solving a puzzle where all the pieces are already on the table. In this kind of case, I can easily look at past temperatures, say 12 degrees, and find similar clues from before. I stay inside the known space, inside the safe zone of my data. That's called interpolation. I'm making predictions within the range I've already seen. But when I look at time alone, things change. The clues from the past stop where my data ends. And now I'm being asked to predict what comes next, to step into the unknown. This is what we call extrapolation, trying to guess what lies beyond the evidence I have. And trust me, that's a whole different kind of danger. In regression, I work within the neighborhood. In time series, I leave the city and head into the woods with nothing but a flashlight. So while time looks like just another feature, it's not. It carries memory, momentum, and mystery. That's why time series problems are harder, because they're not just about relationships between features. They're about how things unfold across time. All right, I had my suspects. trend, seasonality, cyclic patterns, and noise. I had cracked the difference between simple regression and time series. But now, I was drowning in data. Every new clue was making things murkier, like trying to spot a shadow in the fog. That's when I remembered an old trick from my early training. When things get too noisy to hear the signal, you smooth them out. You don't chase every tiny fluctuation. You step back and look at the bigger picture. Let me explain. Imagine you take the first 7 days of ice cream sales. Instead of looking at each day, you average them together. Then you move forward 1 day and average the previous 7, and so on. What you get is a smoother line, something easier on the eyes and more honest to the pattern underneath. Sure, there's a cost. At the very beginning, you won't have enough data to average, so you lose a few entries. Or you can reduce the window, but then the line gets a little bumpy again. It's a trade-off, but one worth making. Let's go back to our good old ice cream sales. The raw data already shows a clear trend, but with smoothing, the line becomes even more graceful, like seeing the story unfold without stuttering. Now take weather, for example. That seasonal back and forth, warm, cold, warm again. A smoothed version lets us see the repeating wave without being distracted by every small change in temperature or unexpected rainy day. Then there's the market. Stocks going up, crashing down, recovering again. Smoothing doesn't remove the chaos, but it helps you feel the rhythm, like spotting a heartbeat in a storm. And finally, pure noise. Website traffic from some failing campaign. No trend, no season, just dots jumping everywhere. Smoothing tries. But the truth is, there's nothing meaningful here. Smoothing is like cleaning your glasses. The raw data might be the truth, but it doesn't always help you see clearly. And when you're solving a time series case, clarity is everything. All right, folks, let me show you what I did next. I wanted to check if I was close to cracking the case or just chasing my own tail. So I used a very simple tool. Nothing fancy, don't get scared by the name. Polynomial regression with degree 1. That's just a grown-up name for basic linear regression. A straight line. That's it. I took the last 5 data points from my sales data and put them aside, like a secret test. Then I fit a line using the rest of the data. Simple, straight, clean. After that, I brought those 5 points back and asked my model, what do you think happens here? And lo and behold, the predictions were close. The line hit almost right where the dots landed. I felt good. Too good. I thought I cracked it. But then, something felt off. I asked myself, am I really solving the case, or just drawing a line and pretending it knows the future? So I went a step further. I asked my model to predict the next 5 future days, beyond what I had, and guess what? The line just kept going. Straight, as if the future was guaranteed to follow the same path. That's when it hit me. I was falling into the trap of the trend. You see, fitting a straight line on past data will always give you a clean prediction, but if all you're doing is riding the trend, you might miss what's actually coming. Maybe the trend shifts, maybe the sales drop, or spike, or wobble, and since I only use time as a feature, I wasn't adding temperature, holidays, ads, nothing else. My model was just echoing the slope of the line, not the truth behind the line. This isn't forecasting. This is extrapolating a trend, blindly. And in time series, that's dangerous. You don't follow the line. You follow the evidence. Okay, maybe the straight line was too simple. So I decided to get clever. I upped the power, went for a degree 13 polynomial regression. That means instead of a straight line, I got this nice bendy curve. Fancy looking, intelligent even. The curve seemed to fit the past perfectly, like it had danced through every twist and turn. A masterpiece. Then I brought back my test data, my trusted 5 red dots. And guess what? The curve completely missed them. Like a blindfolded detective trying to hit a dartboard. The predictions were way off. And then, just for fun, or maybe pride, I asked it to predict 5 more future points. And sure enough, the curve just kept curving. as if the future was destined to follow its poetic bend. No questions asked. Wait a minute. What am I missing? What am I failing to understand here? More power, more complexity, and yet worse predictions. Maybe I need to think just 5 seconds, just me and the clues. I was back in the field trying to make sense of the ice cream sales data, but something was off. Some weeks the numbers barely moved. Other weeks they were jumping all over the place. It was like trying to follow a whisper in one room and a scream in the next. The variation, the ups and downs, wasn't staying steady. It was changing, loud here, quiet there. That kind of noise can ruin a good investigation. Visually it's easy to spot. But as a detective I don't just rely on my eyes. I need proof, numbers. I need to measure if the variation is changing. I stared at the numbers. They were everywhere, like scattered clues at a crime scene. Some high, some low. I needed to know just how scattered are they. That's when I pulled out a familiar tool, the ruler of chaos. Variance. Variance tells us how far the numbers are from the average, or in detective terms, how wildly the clues are dancing around the truth. If they're close together, variance is low. If they're all over the place, variance is high. Simple. Let's calculate variance for first 5 sales data points. First, find the average of the values, the center of all the clues. Now we ask, how far is each clue from the center? Then square it, because distance matters and squaring gives weight to larger deviations. Then plug the values into the formula for sample variance and we get variance of these 5 data points. In similar manner, we can calculate the variance of our entire series. Do not expect me to calculate this in front of you. I entrust your computer as much as I entrust my mind to do this. So there I was, sitting with my answer, 5338, 135, the sample variance for the entire series. But then a thought crept in. What does this number actually tell me? Is it low, high, suspicious, calm? It's just a number, sitting there. No context, no comparison. And a detective without comparison is like a torch without batteries. Visually, I could feel it. Some parts of the time series felt calm, others wild. But mathematically, how do I prove that? How do I turn this gut feeling into cold, hard numbers? Tick, tock. My mind was racing. Then it hit me. What if I split the entire series in 2? Just slice it down the middle, first half and second half, then calculate the variance of each part separately. Now I'm not just holding one number, I'm comparing 2. I'm asking, is the second half more chaotic than the first? Is the story getting louder or calming down? If both variances are similar, I might be dealing with steady noise, a reliable suspect. But if the second half is much higher, maybe the situation is heating up, a twist in the tale. And if the second half is calmer, then maybe the storm already passed. This is how a detective works. You don't just trust your eyes or numbers alone. You ask them to talk to each other. You break the case into pieces and compare. Turns out, variance isn't just a number. It's a story, one that changes, one that needs context. And I just found a way to listen better. The second half of the series was noisy, way noisier than the first. The numbers didn't lie. The variance had almost doubled. But could I trust this split? Could one division tell the whole story? So I thought, what if I break it down even more? 3 parts, 4 parts, check the variance in each. But then another voice in my head whispered,
Detective, this feels arbitrary. You're just slicing without a plan. Is this standard?
and the voice was right. This wasn't standard. I was manually chopping the story without thinking about the rhythm of the data. I needed a better lens, a smarter magnifying glass, one that could move with the flow. I needed something rolling. That's when I discovered a better method, rolling variance. Here's how it works. You pick a window, say 30 days, and slide that window across the timeline. At each step, you look at just those 30 values. You calculate variance in that slice, then shift by 1 day, drop the first, pick the next, and calculate again. This way, instead of one number, you get a whole new series, one that shows how variance is changing through time, like watching noise levels rise and fall on a moving graph. Think, how do you choose the window size? Answer is, no one size fits all. It depends on your data, how much you have, and what kind of story it tells. In my case, I had 100 data points. A 30-day window felt natural. That's about a month. Enough to capture small changes, but not too small to overreact to every little blip. Too small a window, too jumpy. Too big, too smooth. The trick is to match the window to your storyline. And just like that, the chaotic voices in my data started making sense. I could see the tension rising before the summer sale. Calm weeks after a holiday. Bursts of volatility out of nowhere. All in clear view. Our rolling variance is rising constantly. And that's not a good sign. A wild clue trail like this? It makes it hard to predict anything. The noise keeps changing. And I can't trust my line of investigation. So what do? Well, we transform the series. That's right. We try to bend it into a shape that behaves better, like putting a restless kid to bed. Now look, there are many kinds of transformations. Log, square root, Box-Cox, you name it. But let's just try one for fun. The good old log transformation. We'll take the log of every value in the series. Just like that. Why log? I'll explain in a bit. Promise. But sometimes as a detective you have to jump ahead to follow the rhythm, then take a couple steps back to explain your moves. You'll see why soon. Now we calculate the rolling variance again. For both series, the original one and the transformed one. Visually they both look kind of noisy. So how do we compare which one is better? We just need to look at the variance of the rolling variance. That's right. Take the rolling variance for each series and then calculate how much that changes. We call this variance of the rolling variance. Genius, right? And guess what? The log transformed version had a much smaller value, much smoother, much cleaner. But wait, how can I compare the variance of two different units? My original series is in sales, maybe in dollars or liters of ice cream, so the variance has units like unit square. But the log series? That has no unit at all. You can't compare a squared unit with a unitless number. That's like comparing the taste of chocolate with the weight of a watermelon. So, I take a step back. I ask, is there a unit-free way to compare variability? Yes, there is. The coefficient of variation, CV. It tells me how big the variation is relative to the size of the data. Now that is a fair comparison. We apply the same rolling window trick, this time calculating the rolling CV instead of variance. Now we've got two new series. One shows how CV is changing in the original data and one in the log transformed data. And now, for the final check, we calculate the variance of the rolling coefficient of variation. Yes, that's a mouthful, but hey, I didn't name these things. I just use them. And this final number? It tells me which version of the series has more stable variation over time. Whew, that was a ride. But see, this is why they pay me. Not to assume, not to guess, but to test every hunch. And yes, sometimes even take the variance of the variance of the variation. Don't worry if that blew your mind a little. Rewind if needed. It'll get clearer with every watch. Huh, I knew it. I knew this would happen. Taking the log almost always helps reduce variance. It's like a detective's secret weapon hidden inside the coat pocket. When the clues start jumping too high, you don't yell, you just transform. See, the thing is, I've been in this game long enough to know how time series behave. When the ups and downs keep stretching farther apart, that's your cue. Log transformation calms the storm, brings wild trends into balance, makes the invisible patterns visible again. It's not magic. It's not luck. It's knowing your suspects. And in this case, variance was the noisy neighbor, and log the soundproof wall. Ha! I knew this would happen. Log transformation, my go-to move. It almost always brings the chaos under control, like a calm whisper in a noisy room. But hold on. Is this really the one solution fits all? What if the series has negative values, or even zeros? Haha, don't panic. This is still a teaching video, not a crime thriller, and the solution is quite simple. Trick number 1, shift the series before log. We can just shift the entire series upwards. Add the absolute value of the minimum number to all points. For example, suppose our series is this. Now, minimum value in this series is 2. So if we add 2 to each element of the series, voila. The series is now positive. The shape remains the same. And now log can do its job. But there's a catch. Suppose I want to compare 2 days. Original difference. From 3 to -1 is a 133% drop. But in the transformed version, from 5 to 1, that's only 80%. See the problem? We haven't even applied log yet, and the relationships between numbers have already changed. That's risky, especially if we're later building models that depend on these changes. Also, what about zeros? Log of 0 is undefined. Boom. That's another hole in the floor. So people add tiny numbers like 0.00001 to sneak past it. But again, it shifts relationships. It's like nudging a fingerprint just to make it fit. Any transformation that changes values will also shift relationships. And when you're solving a time-based case, you can't afford to lose that trail of clues. So be extra careful. Let's talk about alternatives. Okay, log transformation is good, but not always perfect. So what if I told you there's a smarter trick, one that doesn't guess the transformation, but calculates the best one for you? Enter Box-Cox transformation. Now listen carefully, because this is the part where detective work turns into a math game. Box-Cox takes your data and tries a range of transformation powers, called lambda, from say 5 to +5, and for each L, it reshapes the data using this formula. So lambda equals 1 is the original data, lambda equals 0 becomes log, lambda equals 0.5 is square root, and so on. But we don't just pick one and pray. We test every lambda to see which one makes our data most normal looking. Repeat, most normal looking. And how do we measure most normal? We use something called the log likelihood function. Basically, for every lambda, we check how likely the transformed data is to come from a normal distribution. Sounds heavy? Let me simplify. Sigma lambda square is variance of the transformed data log of y, is the adjustment for the transformation's Jacobian, and log L lambda is score we're trying to maximize. We try each lambda, compute the score, and the one with the highest log likelihood, that's our winner. That's the lambda we use to transform the data. So yes, you don't need to keep guessing powers manually. Box-Cox handles it all behind the scenes. But there's a problem. Again, Box-Cox can't handle 0 or negative values. The moment it sees one, boom, the math breaks. So if your data has those, you're back to shifting the series. And we already know, shifting messes with the original relationships. Now, if your brain is starting to work like a real detective, your eyes should be stuck on that formula. Let's look again. One thing in there is wrong, and one thing in there should set your neurons on fire. Let me ask you a question. Look at that formula. If lambda equals 1, shouldn't the result just be y? I mean, shouldn't the Box-Cox transformation just give you back the original value? But it doesn't. Try it yourself. See, this is not a bug. It's by design. The goal of Box-Cox isn't to return to y when lambda equals 1. The real goal is to make sure the function behaves smoothly and continuously as lambda changes, especially around lambda equals 0. It's not about recreating y. It's about building a family of transformations that transitions neatly from power functions to the logarithm. The Box-Cox transformation is centered at lambda equals 0, where it becomes log y. That's the heart of it. Everything else is designed to be mathematically neat around it. Want the original y back? Use the inverse transformation. That's how you reverse the effects. Not by expecting lambda equals 1 to magically hand it back to you. Coming to the second statement that negative values break the math, now here's the part where Box-Cox really breaks. The moment it sees negative values. Let's say y equals -1 and lambda equals -2. Then y power lambda equals -1 raised to the power of -2, which gives 1. Seems fine, right? Now try. Lambda equals 0.5. Boom! Math explodes. Now, if you're thinking imaginary numbers, well, great. But your machine learning algorithm is not. These models work in the realm of real numbers only, and they refuse to touch anything imaginary. So what do we do? Meet Yo Johnson, the upgrade. Now here's the real superhero transformation. Yo Johnson. It does everything Box-Cox does, but also handles zeros and negatives like a pro. For positive values, it's just like Box-Cox on y+1. For negative values, it applies a mirrored transformation. Handles all values safely, no shifting required. Remember this. Every transformation you apply changes the series. Some do it gently, others mess with the shape. Your job is to preserve the story while calming the chaos. If you can help your data become more stable without distorting its nature, you're not just cleaning it, you're respecting it. That's the real art of time series transformation. All right, here they are. All the suspects lined up, the transformed series, with the variance of their rolling coefficient of variation proudly printed like criminal records. Take a moment, let your eyes adjust, look closely. Clearly, log transformation seems to have done the best job, the lowest variance of rolling CV. But do you think I gave you a minute just to spot the lowest number? There's something more important here. Even if log's number had been slightly higher than, say, Box-Cox, I still would have chosen log. Why? It's about balance. This decision isn't just about numbers, it's about balance between how much the transformation stabilizes the series and how easy it will be to reverse later. Log transformation is elegant, simple, and when it works well enough, I'd rather stick to it than introduce a more complex, harder to invert transformation like Box-Cox. That's the key word here, slightly. Don't go berserk and throw log transformation everywhere just because it did well once. Sometimes simplicity wins, but only when it wins enough. I took the original series and with log transformation chosen, I now bring out the model again, the polynomial regression with degree 3. I train it again, test it on the last 5 known points, then predict 5 steps into the future. But now, I do something new. I reverse the log transformation on the predictions to get back the real-world values. But something's still off. The predictions, they're still way off. Now I've got clean, stable data, a solid transformation, a higher degree polynomial, and yet the model fails to predict what comes next. So what exactly am I missing? The data may look stable now, but are its rules changing over time? Okay. I cleaned the noise, I transformed the series, I even polished the curve with a polynomial brush. And still, it doesn't work. Something's still off. And then it clicked. It's not about what I can see, it's about what's sneaking underneath. There it is, the trend, hiding in plain sight. A slow, steady climb, like a thief walking upstairs one step at a time. In detective terms, trend is the habit of the data, the behavior that doesn't change quickly. If sales are going up by RS10 every day, that's a trend, like a suspect who walks the same path every morning. Let's say we're tracking daily earnings from an ice cream cart parked on a beach. Here's the data. Whoa, every day it increases by RS20. No randomness, no pause, just a straight-up climb. To remove that climb, the trend, we subtract each value from its previous value. Aha! See what happened? That lazy upward walk is gone. All we see now is flat change, constant, predictable, trend removed. This is like asking not how much you have, but how much more you earned than yesterday. And when that value becomes stable, I know the trend is no longer hiding in my data. Let's take a more realistic case, with noise added. Now it's not just a staircase. It's like stairs with a few pebbles. Upward climb, but not perfectly. Interesting. This time the changes are not all the same, but they're now telling me the story of daily movement, not the overall path. That's the whole point of differencing. We stop watching the road and start watching the footsteps. So, here's what we did. Clue seekers. We spotted the suspect. Trend. We used a tool. First order. Differencing. We turned the series of values into a series of changes. And remember, detectives, if your data walks too calmly in one direction, it's probably hiding a trend. All right, it's time to return to where it all began. Ice cream sales. My first suspect. My first crime scene. And this time I'm going in prepared. So here's what I did. I took the original series again. The raw timeline of sales. My clues. I applied log transformation to clean up the roller coaster of variance, just like before. But here's the twist. Instead of rushing to fit a polynomial curve, I paused. I waited. I remembered the suspect. Trend. So this time, I hit it first. I took the first order difference of the log transformed series. This removed the steady climb, the gentle push upward that had been quietly ruining my predictions. Then, with the differenced series in hand, I brought out my model again, a polynomial regression, degree 3, not too simple, not too wild. I trained it, tested it on the last 5 known data points. It behaved well. I pushed it further, predicted the next 5 unseen values. It held its ground. Now to bring everything back, I needed to reverse the differencing. And that's simple. Whatever value I just predicted, I add it back to the last known real value. One step at a time, walking forward. Do remember to inverse the log transformation as well. Voila. Look at that. Much better. The model isn't blindly following the trend anymore. It isn't getting distracted by noise. It's actually predicting like a seasoned detective, by looking at changes, not just positions. Now, you saw me take the first order difference of the series, right? A powerful move to get rid of that slippery suspect, the trend. But let me ask you something. Did you notice what I lost in the process? Take a moment. Look at the numbers, before and after. What happens to the first data point in the series? To calculate the difference, I subtract the previous value from the current one. But what will I subtract from the first value? Exactly. Nothing. There is no previous value. And so, we lose it. Silently. The first value disappears like a witness who never showed up to testify. Now, if you're working with 100 or 1,000 data points, losing one feels like dropping a grain of sand on a beach. Meh. Who cares? But what if you have only 20 data points, or 10? Suddenly, that one missing point is 5%, 10%, even more of your total data. In small data sets, every clue counts, and dropping even one could be the difference between solving the case or being misled. Oh, always remember, differencing is a brilliant technique, but not free. It costs you a data point every time you use it. Use it when you must. Avoid it when you can. Always weigh the trade-off between preparing your data and keeping it whole. We've been on this case for a while now. We cleaned the noise. We caught the trend. We controlled the wild swings and variance. We differenced, transformed, tested, and retried. But all of that was to reach just one goal: to make the series stationary. Because unless a time series is stationary, I can't question it. I can't model it. I can't predict its next move. Not fairly, at least. What does stationarity even mean? Let's break it down real easy. Stationarity means the average behavior, the mean, stays the same. The amount of variation, the variance, stays the same. The relationship between past and present, the autocorrelation, stays the same. In plain words, the rules of the game do not change over time. Can we see if a series is stationary? Now, of course, I could throw complex statistical tests at it, but I don't have all day to explain the math behind those. Let's keep it real. Visual check for stationarity. Look at the trend. If the line is steadily going up or down, that's a red flag. Trend detected. Check the spread. If the ups and downs, height of the line, get wider or narrower over time, variance is changing. I thought I'd cuffed them all. Trend, noise, variance. But then, just when I was sipping tea, he came back again. Same time, same behavior, same motive. Just like last time. This one isn't new. He's been here before. And he'll return again, like a ghost from the past. Seasonality is a repeating pattern in the time series. It's not random, it's scheduled. Example. There's no trend, no variance shift, yet something keeps repeating. This repetition makes the series non-stationary. Again, there's no upward or downward slope, no trend. The swings are stable, so variance is fine. But look at that pattern, up, down, repeating every year perfectly, predictably. And that makes it not stationary. Because the mean value changes depending on when you are. June has different average than August. That's a moving mean. That's a red flag. Let me show you how we deal with this suspect. Take the value from today and subtract the value from the same time last year or same period ago. This removes the repeating pattern, like removing a mask. What's left is the real fluctuation underneath. Just like first-order differencing removed trend, seasonal differencing removes seasonal patterns. If I don't remove this cycle, my model will get confused, thinking the ups and downs are random when they're actually routine. By seasonally differencing or decomposing, I level the playing field. Only then can I make my series truly stationary. Trend is gone. Variance is steady. Seasonality's been dealt with. Now, and only now, I can begin to forecast, because the suspect can no longer hide. The series is stable, predictable, stationary. Just when I thought I'm making progress, the client walks in with doubt.
Detective, all this looks like just trend, up or down depending on where you start. Can I really trust these findings?
Ah, I see where you're coming from. But don't worry, I haven't finished yet. I'm just tired. You're right. The trend you're seeing is from those polynomial regressions I've been using. They help visualize, but they're not the sharpest tools for prediction. Tomorrow I'll pull out the real statistical machinery, the clean, crisp kind. The kind that doesn't just look at the curve, but at the structure hidden inside. We'll look at autocorrelations, generate a few smart features, and study how the series behaves under the hood. But for now, let me breathe. A tired brain, a cold cup, a solved case. All I need now is a like for coffee, a comment for the donut, a subscribe for the couch, and a share to file this report with the department. Do your part, partner, and I'll be back on the case tomorrow.